This video will cover the topic using the first and second derivative to determine graph behaviors. Let's look at the function f of x equals x squared. We know that the first derivative is f prime of x equals 2x, and the second derivative is f double prime of x equals 2. We also know that the graphs of these functions look like this. The graph of the original function is a parabola. The first derivative increases linearly, and the graph of the second derivative is constant at f of x equals 2.
So what are the relationships between these graphs?
To get an understanding of this, let's first analyze the graph of the original function. We can see that if we read the graph from left to right, the graph is decreasing until it reaches 0, 0, after which it begins to increase. This is translated in the graph of the first derivative, f of x equals 2x. As we can see, the graph of the derivative is negative until it reaches x equals 0, where it becomes positive. Observe that the graph of f prime of x equals 2x is below the x-axis to the left of the y-axis, therefore negative when x is less than 0, and the graph of f prime of x 2x is above the x-axis to the right of the y-axis, therefore positive when x is greater than 0. We can summarize this with the following chart. When the graph of the original function is decreasing, the graph of the first derivative is below the x-axis, meaning the first derivative is negative. When the graph of the original function is increasing, the graph of the first derivative is above the x-axis, meaning the first derivative is positive. When the original function changes from decreasing to increasing, the first derivative equals 0. This point is called a critical point.
What about the graph of the second derivative? What does that mean about the original function?
That's a great question. In this case, the second derivative is a positive constant, which tells us about the concavity of the function.
What is concavity?
Concavity is the shape of the curve, and it can be defined in two ways, concave up or concave down. In this example, the graph of f of x equals x squared is concave up, whereas the graph of f of x equals negative x squared would be concave down. The point where the graph changes concavity is called the inflection point. A useful tip for remembering this is that concave up makes a smile and concave down makes a frown. We can use the concavity to determine information about the first and second derivative of the original function. In our example, we have an original function that is concave up, so our first derivative is increasing and our second derivative is a positive constant. What do you think would happen if our original function was concave down?
Would it be that the first derivative was decreasing and the second derivative was a negative constant?
That is correct. We can summarize all of this information in a few statements. When the original function is increasing, the first derivative is positive, and we cannot determine anything about the graph of the second derivative. When the original function is decreasing, the first derivative is negative, and we cannot determine anything about the second derivative. When the original function is concave up, the first derivative is increasing, and the second derivative is a positive constant. When the original function is concave down, the first derivative is decreasing, and the second derivative is a negative constant. Additionally, the original function has a critical point where the first derivative is equal to 0, and an inflection point where the second derivative is equal to 0.
Will the second derivative always be a constant?
Not necessarily. There are times when the second derivative is linear or parabolic. It all depends on the exponent in the original function. We will go over a more complex example problem in the video, using the first derivative to find critical points and the second derivative to find inflection points.